Hi there. Right, it looks like we've got a full house. Are we live? We are live. Right. Let's make a start. Okay, just a quickie. Who have we got here? We've got. Please announce yourself if you can, and if somebody is listening with you and can't, just check in. Please let me know that you are there. It's just for the register. So I've got Callum, Corey, Georgie, Declan, Charlie, Amy, Regan, Luke, Harry, Sam, and Brett. Very good afternoon to you guys. Anybody else, please make sure. Nick, good morning. Good afternoon. Sorry. How many are we? So yeah, almost there. Okay, we're going to make a start. It's not going to be a long presentation. You may be pleased to hear. It's just covering those three criteria: 2.5, 2.7, 2.8. I'm not sure about 2.6. Should be covered in here as well. I think it's just a typo. And I think 2.5 and 2.6 has been covered with the previous unit as well, but not 2.7, 2.8. So that's where it comes from. Okay, just let me have a look at the controls. Everything looks okay. Ross is watching. Good. Hi, Ross. Thanks for the update there. Okay. So anyway, let's go through the presentation. It's not very long. It's just short, so we should be done in about half an hour or so. Then I've just been working on the just a summing up of 315. So we're going to go through the unit one more time. It's just like a concise, condensed version, and putting it all in a nutshell about motors, three-phase motors, and so on. And then you should be ready for the assignment as well. Okay, which keyboard? That one. Hi, Ryan. Good to see you. Just seeing your name come on. Thanks for checking in. These are 2.6 as well, so we've got 2.6 as well. Must be a typo with the 2.5, 2.6 before, like when you look on the screen before. So it's the last three criteria which we are covering in this unit. Okay, how measurements can be affected. This session really should be a parallel it should be a practical session, and it would be a lot easier to just give you a couple of DMMs and then have some circuits and then do it for yourself, and it would make much more sense than me talking to you. And there's a good chance you don't retain. I mean, it's normal. When you listen to a talk, you retain just a few percentage points, about 5-10% or something. So it's not that much. But anyway, you can refer back to this presentation. They'll all be uploaded, be made available to you, so you can go back to it. Okay. Measurements can be affected. So other components connected in parallel to the item tested. So that's one of the first aspects where measurements can be affected. So we've got a battery here. Yeah, we've got like two LEDs, and these two LEDs is just to show you what it means for parallel connection. So they are connected in parallel to one another. Yeah. So if I put a meter across, like a meter that's not very good, if I take a measurement, effectively it would be like another bulb I put in the circuit. So some current is drawn from this circuit, and that will affect the reading as well. And so when you take a measurement, the moment you're measuring something within a live circuit potentially can affect the reading. And obviously the important thing is for you to gain the understanding that you understand that this is happening and that you are aware of it. So whenever components are in parallel, and you try to get a reading about the component, that reading is not going to be spot on, but it's going to be skewed slightly or massively. Right, next one. Hayden, good afternoon. I'm just acknowledging that I see you on the script. It's thanks again for checking in. Again, important, very important for me, so I can reconstruct the registers when they come up live. Okay, how measurements can be affected. Okay, a couple of other things as well. One of them, which I'm sure you've seen at your work, is when you've got dirty contacts. So dirty contact can affect the measurement significantly. When you put your leads on the contact, you may not get any reading at all. It may just give you For example, when you measure for resistance, just an open circuit, or if you try to pick up a voltage, you may not get a voltage. And again, with experience, it sort of comes to you slowly. What I tend to do is when I've got a meter and I don't get a reading, I start scratching a little bit with the probes. And you've noticed the probes are quite pointy as well. They've got quite a proper probes, quite a vicious pointy bit right at the front of it. So I tend to scratch a little bit and to make sure that there really isn't a voltage, or there really isn't anything present, or if I measure for resistance, to make sure I'm getting a real reading. There's another one as well, and this is the uses for earth fault current testing. And the use, and it's normally used in pad testing, and it's a big issue. So in the past, you had a current which was somewhere between 4 and 25 ampere. So it's quite a huge current, and you put it through the ground lead or the earth lead to test the integrity of the lead, making sure it doesn't fail should there be an earth fault current going through. And one of the problems has always been that, or not a problem, but when you sort of take your probes on, you get a little bit of a spark, and it's almost a bit like a magnet as the current pushes from the probe through the conductor, down to the other side where the earth connection is. And there's always been something like a contact current. And what's happened over time, the pad testing equipment, they reduce the current to go through. So instead of using 20 ampere, they just use 1 ampere or 100 milliamps, just to make sure that the connection between earth and whatever you're testing, the outside, what you're testing is there. But the readings are quite skewed up, so you do get a higher resistance reading. So you might get a reading for 2 or 3 ohms, whereas once you put the full current through, that reading would go down, and they call this like a contact current. So you need a contact current. So what they've done now is they've got really intelligent pad testing equipment, which initially generates very high current of about 10 or 20 amps or something, and then it drops down just for a moment, for a couple of milliseconds, to establish the contact, and then it drops down to 100 milliamps or an amp or something lower, and gives you the reading. So that's they do this just to establish the initial contact to get through. Callum said something interesting. Just clean it with your fingers. That's what I was told. Okay, is one thing, but one thing you have to bear in mind is there's grease on your fingers, potentially, and grease could have insulating properties as well. It's just something to bear in mind. But obviously, it's clean it up as best as you can with your fingers, or if you've got an overall or whatever, or just for the contact to move the dirt away to get a contact. It's important. Thanks for the contribution, Callum. Right, other keyboard. Our measurements can be affected. So there are a couple of other things as well. There are inside and outside conditions you need to be aware of. So obviously, what you tend to find when you deal with installations that are outside is that you've got a lot more issues with corrosion and again, environmental dust and dirt. So again, when that takes place, you may have to clean up the contacts before you can take a measurement. You've got dust as well. A lot of dust is insulating. So when you've dust settling down, you take a measurement and you're just sitting on top of the dust. It could affect your measurements. And then you've got another nightmare, which is conductive dust. And I came across this when I was working in steelworks, and I had to work with machines. And every now and then, some of the machines, they stopped working. And the workaround was, instead of taking the machine apart and calling the service people out, they just got compressed air and gave it a few blasts of compressed air across the contacts, and then the machine magically came back into action. And that's what I was told to do at the time. And the problem they had was just the machines were grinding metal, and there was metal dust all over the place. It's like when I was done by the shift, I was covered from head to toe. Even it went through my overalls as well. in steel dust. It looked like a miner, but it wasn't coal dust. It was just steel dust. Again, did we have PPE? We had PPE. I mean, I had some hearing aids. I put the earplugs in, and like the massive headphones things as well. We had dust masks, to keep the dust out, but I didn't find that they were very effective. And it's like at the end of the day, you were coughing up metal dust. It was just vicious stuff. The problem is when you're in this environment, dust gets all over the place, and there's nothing you can do about it. And some motors as well, they've got a little fan inside for cooling, and they would just pull the air, the dusty air, through the motor, potentially with the dust settling down all over the place. Real nightmare when you're dealing with that. Right, Amy and Georgie, thanks for that, for the update about Joe. Hi, Joe, as well. Okay. Corrosion on surfaces used for testing, so that's a biggie. And then we've got another problem, and that is uncalibrated equipment. Depending on what you're testing, whether you just test for the presence of a voltage, or you really need to know that, for example, when you've got testing equipment, part testing equipment, or insulation testers, it's of the essence that if you do a 500 volt insulation test, that is not 410 volts, but it needs to be 500 volts. So an easy calibration is you use a meter you know is precise. And how do you know it? It's a problem as well. You may have to get like a standard voltage, which is used to then calibrate the meter, and then you take the meter and you measure the voltage from the insulation tester to make sure that it goes up to 500 volts. I mean, that's one of the things. I remember when I was working in telecoms, the way we did it, we had one crystal oscillator, and the important thing was we were sort of going on sites, and we had like radio equipment which went throughout the site. So there might have been a repeater station, like what you use with your mobile phones, like a relay, a phone repeater, but just for radios, two-way radios. And we had loads of radios throughout the factory, and basically what we said is we had one crystal oscillator, and I'm not sure what it was tuned to. I don't remember. I think it was 10 megahertz or whatever. And when we tuned up the testing equipment, so we had a few testing equipments, we used this crystal oscillator and we tuned it in. And we didn't care whether this oscillator was out by by a couple of hertz or whatever, and it didn't really matter either, providing everything on the factory floor was tuned towards this oscillator, towards the precision of this oscillator. So for example, if you imagine everything is 1 kilohertz out, which is not the end of the world, you're not infringing on the neighboring channel or anything like that. So the channel shift was about 25 kilohertz. If you were 1 kilohertz out, and providing it was on everything throughout the factory, everything would just work fine. It would just be slightly out. And that's again the way we used it where I was working for this telecoms company, where we used calibration. So we had one standard, and this standard was used throughout all of the operations, and that was sort of the holy grail. I think it was reasonably precise, the reference, the frequency reference, and but based on that we could use this. And I guess it's similar as well. When you get a standard, you can then calibrate your equipment against this standard, and make sure that you get precise readings. Is it critical? I don't. I think a lot of instrumentation you get today is very precise. You don't have the inaccuracies you had about 30 years ago. So if you get like a top-notch meter from Farnell or whatever, you can be reasonably confident that whatever you measure is right. It doesn't do any harm to compare it to other meters. I sometimes do it here. I've got like umpteen meters. So when I measure something, I take one, take another one. And you can see there's sometimes slight differences. Nothing critical. It's just like a few percentage points out here or there. And for the type of work you are most likely going to be doing, I don't think if there's like a tolerance of a couple of percentage points, it is that critical. Can't think of a scenario where you would need to be spot on with your voltage measurements or resistance measurement. Right, battery failing. Good one, good point. I'll be talking about. I think it comes up later on in the presentation, but that's a biggie. Did I mention it last time? I don't know. Whenever you've got a meter, you should always have spare batteries. And most of them, they use these 9-volt batteries. Some meters, they've got like these weird specialist batteries. I know the AVO has got a specialist battery. So you should always have a few of them around and have a few fuses as well for your meter. So just in case you make a mistake or an error and the fuse goes, and you can't use it for current measurement anymore. Right, next one. Okay, equipment calibration requires a proven voltage supply or resistance or frequency. We just talked about this. Equipment is calibrated against a known precise source. Yeah? So it's for V or R. You can see some of the, I've got a picture here on this, if you just follow the mouse. You see some of this equipment here, and you are talking, when you get this equipment for calibration, you're talking huge amounts of money. So it's sort of £1,000 upwards, £10,000 and more. I remember the equipment I was working with when I repaired radios. The testing equipment costed about £20,000, and at the time you could buy a house for £20,000. Yeah. So this is like a terrace house or something. You could buy one for that sort of money. So I'm talking like the late 80s. Right, next one. Calibration equipment frequencies you need to consider. So frequencies, I don't mean the frequency, but the intervals. Maybe I should use intervals. So very often there's a manufacturer recommended calibration interval for sensitive equipment where it's important that you have your equipment calibrated. There's before and after a major critical measuring project. Yeah, so if you measure something or you've got like a project which is very critical, where everything needs to be spot on, everything needs to be at the top frequency, at the top voltage or whatever, it needs to be, calibrated to the point. Then you should do it before and possibly after the project as well, making sure that the equipment is still up to scratch. After an accident, if the equipment got potentially damaged through being knocked, so if you've got an accident, you drop the equipment, whatever it is you're dealing with, or the equipment got a knock or whatever, and then you may think that it's necessary to calibrate it just to be on the safe side. Just to go back on this, if you get a meter, like a DMM or something, I wouldn't even know how to calibrate it. So with the AVO or analog meters, there are little screws inside and little potentiometers where you can actually do some calibration. When you do a resistance measurement with an analog meter, you have to calibrate it anyway. So you have to put both leads together, and then you've got a little potentiometer, and you tune it in for 0, and that's it. You're done for 0 ohms, and that's your calibration there and then. For voltage calibration, there are normally little potentiometers inside the unit you could use to tweak it in a little bit. Digital meter, when you open them up, there's just nothing there. There's nothing there to calibrate it. All you could say is, right, this one is way out, we're not going to use it. Okay, calibration, we're talking really about measurement instruments, but just to put your mind back, when we were looking at the 24-volt power supplies in the PMC, they had like a tiny hole, and I don't know whether you remember this. I tried to draw your attention to this, but it's maybe you remember, maybe you don't, but there was like a tiny hole, and you could put in a tiny screwdriver, and there would have been, again, a tiny screw which is connected to a potentiometer, and you could calibrate there as well, so you could get the voltage up and down. And what you notice as well, we were measuring two 24-volt power supplies, and one had a voltage of 24.1, and if I remember right, the other one had like 24.2 volts. So they were slightly out as well, but you could calibrate the power supply itself. Meter calibration again is a different story, but you can at least verify that the meter is within range. like 1 or 2% or whatever. Okay. Authority for testing equipment. There are different types of test classes, and it's just to go through this a little bit. And I've got lots of health and safety sheets, and you just need to know about this. That's all. Just store it away in the back of your mind. There's so-called SELF, and that stands for Safety Extra Low Voltage, and that goes up to 50 volts AC RMS and 120 volts DC. I think we talked about it last time a little bit. So SELF is supposed to be safe. So if you get a shock, it's unlikely to kill you. At 50 volts, you will feel it, but unless your heart is in a really bad way, it is unlikely to cause fibrillation. There's the issue of working on dead equipment. And it's like the thing, you're an apprentice, yeah. So a certain type of stuff you're probably allowed to do, and there's certain stuff which is a big no-no, or you're only allowed to do it with supervision. So I would think that self-equipment is safe for you to use, and you probably have the authority to use it, but I don't know. Yeah, it depends on your company. When I talk to our health and safety guys, they freak out if I tell them that I want you to work on 12-volt live equipment, on 24-volt live equipment. They hear the term live, and they immediately say, "Oh, health and safety, we can't do this." Yeah. From an engineering point of view, it's complete nonsense. Yeah. The risk is virtually zilch. It's highly unlikely that anything could ever happen to you on a 24-volt system or 12-volt system. And again, especially under supervision, it gets dangerous when you take measurements on 240 volts or 415 volts. Okay, so working on live equipment, there's this term low voltage, and you wouldn't think it is low voltage, but that reference goes to figures below 1000 volts AC. So, and again, I think I mentioned this last time, when you look at 1000 volts, it's where stuff starts jumping. Below 1000 volts, you need to have contact in order to get a shock or to get some current through your body. Above 1000 volts, you don't. You just need to be near it. And I'm not sure whether I did this with you, but I tend to do, when I've got my insulation tester, I tend to do an experiment that I put the probes really close to one another, but they are not touching. And at that point, you can actually see arcs coming over. So if it's dark and you look at them, you can actually hear it. So you hear this crackling of the sparks, and you can see a little arc as well, which comes over. And this only happens when you go up to 1000 volts. At 500 volts and 240 volts, less so, if not at all. Yeah. So high voltage is above 1000 volts. Yeah. So again, you would need a whole set of different authorizations. So the normal Sparky, the normal electrician, will be okay to work up to 1000 volts on live equipment if it's required. Sometimes when you, for example, want to see whether there's something wrong with the three-phase motor, one of the things you might want to test is, do I get the voltage at the motor? If the motor is running, what are the readings? Is once it draws a current, is the voltage dropping down on one of the phases for whatever reason? And obviously you can't do this on dead equipment, so you would do this potentially on live equipment. And then obviously high voltage is above 1000 volts, but you need a completely different set of skills to deal with that. So when you go to a substation or to a transformer station, all you need to be is you need to be near a transformer that is dealing with high voltages. And if you are a good conductor down to earth, you might get a spark that goes right across half a meter, even more, and might kill you. So it's very, very dangerous once you get into the high voltage realm, above 1000 volts. Okay, right, next one. What tests are you allowed to conduct at work? So, for example, working on 24-volt DC circuits, working on dead single-phase equipment, working on unsupervised, supervised, working on high-voltage equipment over 1000 volts, using hand tools from 110-volt supplies. So that's the question to you. Gives me a chance to put kettle on and just let you tell me what you're allowed to do at work. if all of you could just come back just one statement, you know, you can work on 24 onto 40 but not 415 or not over 1000 volts or only supervised, unsupervised. Are you allowed to use hand tools which operate from 110 volts? Okay, the ball is in your court. Let me know. I'm just going to put kettle on. Let's see. Ross, go to any panel when supervised. Okay, that's interesting. You can do that. Ross, you work for Princess, right? Working supervised in dead panels. Okay, right. Some not allowed in panels, unsupervised. Can work on everything else. Okay, yeah. So can you take a measurement from a three-phase motor that's running? Or not running, but that's powered up. It would be running then, wouldn't it? Right. What about the others? What about Coca-Cola? Amy, Georgie, what's the situation for you guys? Are you allowed to work, or is it a big no-no? You can only work supervised, or what is the situation at Coca-Cola? Okay, yeah, makes sense. Yeah. Even low voltage circuits. I mean, are you allowed to work on sensors and 24 volt equipment? Okay. Thanks, Hayden. Mostly supervised stuff, though. Okay. Yeah. A few more responses. Callum, what's the situation for you? Okay. So, Hayden, to use sun tools, have to do training, but need to be qualified to do the training. Okay, fine. Yeah. I know these days it's a lot more restricted. Again, when I was in your shoes, when I was in my 20s, starting in industry. Okay, we are back up. One watching now. Just wait for everybody to come back. Okay, I missed this slide. I meant to actually do it today, but forgot about it. We're almost done with this presentation. One problem is we've got statically sensitive equipment, and it's a big problem. Yeah. So the idea is, so when you sort of work on sensitive equipment and you are just moving around as normal, you can charge your body up to easily by just walking around and doing everyday stuff to about 300 volts, up possibly to about 1,000 volts, and you won't even notice it. So when you're dealing with electrostatically sensitive equipment, you can destroy it without a huff and a puff, and it's just dead. And this is just you touching it, and innocently, without any problems whatsoever. It's important to be aware of this. A couple of points. I'm just going to type them in here. Let's get the right keyboards. Sort of be aware. Let's try again. Be aware that that you can be statically charged to 700 volts without, and that's just static, without even feeling it or noticing it. Okay, if you touch statically sensitive, sensitive equipment, it can be destroyed by simply touching it. Okay. I'm not going to sort of dwell too much on this unit. We're going to deal with this unit when we look at PLCs. I think we've done it, haven't we? If we haven't done it, we're gonna do it as well in more detail. This particular unit where we just look at electrostatic sensitive devices, and it's a big problem. Biggest problem is one of those things where you don't think there's anything wrong, but you, for example, touch the equipment and there are tiny junctions in the microprocessor, and these junctions they don't get fully blown when you touch it, but they just get sort of slightly, sort of halfway blown. But then the equipment is back at work, and you know, a month down the line the equipment fails, and it's just down to possibly you having touched it whilst you were servicing it or maintaining it, and you were statically charged up. So things, if you are aware of, if you know that you're dealing with statically sensitive equipment, you need to earth yourself. There's very simple ways of doing this. If you're in doubt, I mean, the easiest way is just you touch something which is earthed anyway. So if you touch, for example, you're in a factory, you've got motors, you've got conveyor belts, all sorts of stuff, all over the place, which is earth. If you touch any item which is connected to earth, you will discharge whatever static charges in your body instantly. So that's one way of getting rid of any static charge in your body, and then you can start working on the equipment. If you don't do it, it's dangerous. I was talking to one of my students, and he's specializing in this testing, and they were having a lot of, or the company was producing a lot of microprocessor based equipment, and they had a fairly high failure rate, a lot higher than what it should be, and they put it down to people handling devices before they go out to the customer, introducing those so-called latent faults, where junctions are only slightly destroyed, so they're still working, but a little bit extra, and then they're gone, and that's one of the problems. So before handling or doing measurements, Okay, so you either earth yourself quickly before you touch it, or keep yourself earthed, or you get an earth strap, which is just like these little things you put around your wrist and you connect it to something which is earthed. And they normally have got like a mega ohm resistor or something in there, so should anything go wrong wherever you attach yourself to, that it doesn't kill you electrostatically. Okay. Right, okay, we've got a couple of slides and then we're done for today. About half an hour I think we've done so far. Okay, voltage sensitive divisor, proof codes of practice. Okay, here we go. A proof code, low voltage switch. It's just like some stuff I got from the Health and Safety Executive, and it just gives you sort of an idea about different standards. Yeah? So we need to discuss standards slightly. Where do these standards come from, and what do they tell us? So we do have standards about low voltage switchgear and control gear assemblies, code of practice for emergency lighting. So this is all about, how much emergency lighting has to be in the factory, what about the batteries, how often do they need to be checked, and so on. So if you've got a power cut and you need to evacuate the factory, that's what this is all about. You've got your emergency lighting there to lead you the way out. Specification for low voltage control gear, then we've got monitoring maintenance guide for mineral insulating oils and electrical equipment, fire detection and alarm systems for buildings, and so on. Just a few more codes. I'm not going to read through them. Anything particularly relevant to what we are doing here. Code of practice for earthing. We talked about that for 308. You get the years as well when those codes were all coming out. And then we've got a few more codes. Yeah. Okay, I think this is the last slide. A couple of questions. Yeah, whoops, just lost it there. Let's try to get it back up again. And again, here we go. Where can you find codes of practice for electrical installation? What does SELF stand for? List 3 items which can affect measurements. If you don't take care, what could happen to ESD, electrostatically sensitive devices? When and why should equipment be calibrated? Okay. All I'm waiting for is some answers from you guys, and then we are done for today. And I can send you back home. Actually, I could give you this work as homework. Yeah, let's do it this way. Just answer those questions for this afternoon, and then upload them to one file, email them to me, and then we are done at this point. Okay. Already some answers coming through. Do you want to do it now? Do you want to do it later? Okay, so we got the second one, safety extra low voltage. There's another term as well where the S stands for. Sometimes is it, not sure, safety, not sure. There's another acronym which is the S stands for at times. Let me just check it out. Oops. Okay. It also stands for separated extra low voltage. Separated extra low voltage. Yeah. So it's isolated from the high voltage stuff. Okay. To separate extra low voltage, ESD components could get damaged by static. Yeah. Spot on, Amy. Dirty contact is conductive to surface corrosion. Okay. Okay, Amy, that's spot on. What else have you got? Have you answered everything? The 3 items that can affect measurements. Have you got 3 items? Just going through there. Yeah, Hayden, that's spot on. Temperature, internal, external conditions, uncalibrated equipment. Okay, that's for the 3 items. That's fine. Okay. Good. I think we are done. What's the time? 42, 45 minutes. That's okay. It's a good time, even with a system crashing once. Right. Think that's it. Tomorrow I will not see you. I'm doing H&C stuff tomorrow. Hopefully I'll be able to get all the marking done as well. So you check out tomorrow late afternoon. You should find that all your 3 and 9 stuff is being marked. So that's what I use tomorrow for. The next sessions is going to be on Wednesday morning and Wednesday afternoon. So we're going to do 315. The first presentation, hopefully it's not going to bore you to tears, but it's on DC and single phase motors. We've done it for 315. We've done it for 308. We're going to do it just a summary, just to catch up, to make sure that we hit all the criteria points. So the emphasis is slightly different. It's tied up to the 315 criteria points. Then we're going to look at 3-phase motors. Again, it's just a reminder and a summary that's in the afternoon on 3-phase motors. And I think at that point we are done. Okay, at that point I'll just go through the one session through the assignment brief, and then I'll let you loose to do the 315 assignment. Yeah. So that should be done and dusted by. Yeah, I think by Thursday. Thursday you should be able to start on the assignment, on the 315 assignment. Okay, I've got a few more comments here. Amy, equipment should be calibrated before, after a major critical measurement project. Yeah. Michael Ian has ticked off my 309 stuff. Shall I just email you to you rather than one? No, it's okay. I mean, it's 309. Don't worry about it because it's just a pass anyway, Hayden. It gets a bit more critical when it's merit and distinction. I'm not sure how keen Ian is, but then it's a little bit more sensitive, I think. Right, I'll leave it at that for now. We're going to talk about the 315, 308 when you do your submissions. Just email me quickly, and then I'll quickly go through it and sort it out. Okay, Hayden, don't worry about it. I'll check it out. If you've done it, you've done it, so you don't have to worry about it. If he's passed you off, he's passed you off. So don't worry. Ultimately everything has to be on one file. It's just to make the point. So we need to get everything on one file eventually. Okay. Right. Okay. I'll see you on Wednesday. I'll be here. You can email me tomorrow. I'll be in the office all day. But primarily I'll focus on the H&C stuff. So far I've only had one submission, so it doesn't take that long to go through. But it might be a lot more tomorrow. So if I'm not too overloaded with the H&C stuff, then I'll carry on with your stuff and then get everything hopefully done and dusted by. At least 309, get 309 done and dusted by the evening tomorrow. Okay, I'll see you on Wednesday morning. Time about 10:30 to make a start. The presentations are not very long, pretty much like today, maybe about an hour or so. And then, we'll see you then. Okay, have a good afternoon and enjoy the rest of the day. Okay, bye-bye.